Hello, today we're gonna talk about the step of crop modeling development, where you're gonna show some examples how to building a model, and each steps you need to look be careful to make some assumptions and develop a model that's more applied for different purpose. So here to start to have this modeling process and its stages. The first step, we have these model objectives. We need to define the hypothesis. You need to make the formulation and the program. After we have this parametrization, evaluation, and here we have a step that we define as the objective met to look if our model objective could be response by this uh, by this proposed equation and parameters that we define. So if here we have some problem, we need to look if our formulation are wrong, if our hypothesis is wrong or not, and in any step of this one, we can return and make a formulation and the programming again, or to look again for hypothesis to make a new formulation, parameterization, and evaluation, and here to see if in this looping we can find if our objectives are being done or not. If this not work, we have here, we need to reevaluate the objective or find another way to building the model or another way to answer your objective. Okay, now we are gonna looking for each one of these steps here to define the objectives. So based on this information, I define here the modeling process in 6 steps. First, we need to define our aims, define hypothesis, to make this mathematical formulation, make the coding program, parameterization, and the model evaluation. So this is the step that you need to evaluate and look to building a model that you can use or building or define a model to use based in the aims that we are looking. Okay, so to start, the first step is define aims. So here the aims, it's a clear statement or question that define the nature of the model. So here's some example of question that you can do to start to define each model I can use or each model I can start to building to answer these specific aims. Here's some example. Each system will be modeled. You need to look if you have a lot of components in our system. Each system I want to represent, it's a plant, it's a soil, it's the weather, it's the soil, plant, weather system. So you need to look at this to start our model. How will the model be used? It is the proposed. I'm looking for plant growth, I'm looking for crop evapotranspiration, I'm looking for all these things. You need to define this. What's the biggest question to be answered by the model? So I need to look this to define which is the question that I want to answer, what I want that the model give to me after the simulation, to define the complexity and the parameters I need to put in this model to work well when I start to use this model. What problem will be assessed? How good should be the model? So how is the level of error that I accept in my model? So I need to look this. And what are the model's inputs and outputs that I need? So if I have some information that's not enough to put this in a complex model, I can building a model more simple to define this information and get the outputs that I want. So the first step is to look to this, define the aims, to see if I have a model already working for my proposal, or if I need to make some new code programming or new equations to solve my problem. The second step is define the hypothesis. So if I define my M's, I need to define my hypothesis to look uh, what is the main idea from this model. So I need to build this list of hypotheses to start to building the model. So we need to be careful with this point here. We discussed in the last class about the model complexity. I can put a model very complex, but I can get error from the calibration, or I can building a model very simple where I get error from the system. Here we have these models needs to be generalist, but universal models are impossible. This can say to us that I can't building a model too much simple because I wanna lose something from the system, but a model that represents all things, it's not possible because I have this difficult to make calibration and define well this complex system. Another point is that the hypotheses need parameters and driving variables. Here we have example where this model we have the hypothesis that weather condition define the crop development. Crop development affect the leaf area index, and leaf area index associated with weather. We have this effect on biomass that is produced. So here in our system, our driving variables is minimum and maximum air temperature, okay? And we have here also the incident solar radiation. So based on this example here, we have these driving variables. We have here a parameter that is the temperature basal for the temperature base for the crop. Based on these driving variables and these parameters, I have a height here that calculate the thermal time by day. This thermal time will affect the development of the crop. Based on these parameters, I define how many nodes the crop have, and based on this I can define the leaf area index. Based on this state variable, leaf area index, I have this solar radiation amount. Based on the radiation use efficient and these parameters that define the how did the crop respond to this, I can calculate the biomass produced by day. So see that in this simple example, we have at least three hypotheses. Thermal time affected by temperature, we have leaf area index respond to thermal time, and you have biomass production responding to solar radiation and leaf area index. So this is some example of our hypothesis. I need to put a hypothesis that I can prove and include this in the model. And based on this hypothesis, the usable models are those that have parameters and state variables that are easy to measure and observe. Here we have an example of a very complex model. We have here the photosynthesis system. We have a lot of many processes occurring here that is too hard to me measure each process and put the equation for each one of these process in this transpiration CO2 fixation. So this is too hard for us to measure and make this calibration that you want to see in the next slide. But in another way, the leaf area index that I can measure easily by experiment, I can use this to make my model, to calibrate my model, my crop model, and based on this, I adjust and make other simulation. So this is one point that our hypothesis need to be elaborated with a little bit of careful. For example, I know that CO2 concentration will affect this photosynthesis cycle or this other simple this other condition here for photosynthesis, but I can't measure or prove that these are occurring or each value is this process. However, leaf area index, I know that the leaf area index will affect the photosynthesis by the interception of solar radiation, and I can measure this very easily. Uh, Another point is that before I start building a model, I can look for current models to define the hypothesis based on these models and make some assumptions to more simple or more complex condition based on my hypothesis, on my aims to build a model. And here we have an example that we work with this vapor pressure depth sensitivity affecting the stomatal control and affecting transpiration and photosynthesis for 2 cultivars of soybean. In the DSAT crop growth model, we don't have this answer for vapor pressure depth and stomatal control affecting directly transpiration and photosynthesis. But what we did here, we find this paper that Gilbert evaluate the response for cultivar stomatal control for cultivar based on vapor pressure depth. So internal, we building these two equations that represents these two cultivar, and we put this equation to control this limiting factor where transpiration and the photosynthesis were penalized based on the vapor pressure depth. So we not represent the all process, we simplify this, but these have these affect the model simulation the way that we want to do. So in our hypothesis, we know that vapor pressure depth affects stomatal control, that will affect transpiration, the photosynthesis. But we simplify this using a measured value to make this calibration and this using this approach in the model to evaluate how the crops will respond to vapor pressure depth and how this can be used to building a new cultivar for different weather conditions. And after we define these hypotheses, for example, vapor pressure depth controlling the photosynthesis and the transpiration, we can make the mathematical formulation. That is, get this information from hypothesis and to express this in mathematical formulation, where the equation will represent each process that you have in the system and the interaction, and this interaction need to be understood to building this equation in a good way to represent our system. So here we have an example of a system where we can put here as a hypothesis that weather affects crop growth and soil water content, and here came building this relationship where weather will give water to the soil, but we have this plant intercepting part of this water from rainfall, for example, and we also have this crop affecting the soil water content by extracting water through the transpiration. So you need equation to explain how the water from rainfall go to the soil, how the water content is affected by rainfall and the crop transpiration, and in this way you can start to bring this mathematical formulation to represent our system. Another point that is important in this mathematical formulation is the way that I put this equation and how I represent the time across this process. So, for example, in this case, what I represent first, the crop getting water from the soil in a specific day, or and after I can put water in the soil through the rainfall, or first I simulate the rainfall, get the input from rainfall and simulate the water in the soil after the rainfall, and after this process, I calculate the transpiration. So these steps are also important to include in the model, and the researcher needs to look carefully about these steps and what I can do first based in the hour system. So you can make this adjustment to represent in a better way how I can put this through the using equation. And here we have an example for leaf area index, where previously in the maze example, we have the thermal time are affecting the leaf area index uh, like a hypothesis, but here you can put this in the mathematical formulation, where in the first step, I will calculate the daily thermal time for this crop, based in the maximum and minimum temperature and the basal temperature for the crop. After I get the thermal time, that is this accumulation of temperature, I will calculate the new add node by day at the plant based in this thermal time and the phylochrome temperature required by this crop. After I get the rate by day, I update the state variable here that represents the number of nodes at the plant. I get the new nodes from one day plus what I have in the last period to calculate the node. After that, we have this simplification where in function of the main stem node number, I have the plant leaf area by crop. So based in this graph and this equation here, I can calculate the plant leaf area based in the number of nodes. After that, I need to get the leaf area index, where I get the leaf area by plant multiplied by plant density. I can get this leaf area index in the system, define what is the leaf area index for this crop. So I get idea where thermal time is affecting leaf area index, but I know that I can put this in equation how in the way that I represent here for you. So after define names, put our hypothesis, put this hypothesis in equation, I need to put this information in a code program because it's too hard. I make this all calculation by hand because I have this process being repeat every hour, every day, depends on the model configuration, and I need a code program to make this to me. So the crop models get a lot advanced after we have computer to make this calculation, where I can use this mathematical formulation using the code program to make this all calculation for us, and I get this result. For this, a basic principle used by modelers is divide the model in subroutines. That here we have an example from this search where we have a module where we have the weather, another one that I have the management, and another one that I have soil. And inside of each one of these modules, I have different process occurring to make this calculation and repeat this process every day. For example, when I get here in the soil, I have this, for example, soil water, where I have like a file with the equations that define the soil water content, how the crop will get this water from the soil. But in this specific file, I have only information, only the equation for these steps for soil water. For example, I need to calculate the crop transpiration to update my value of the soil water content. So I don't do the calculation for transpiration here in the soil water. What happens is that maybe in the crop or weather condition, I have this calculation and the transpiration is output from weather, but it's an input information in the soil water. So I have this division in the crop model to help us to building the model in a more easily way. And if I need some additions, I don't need to open all the model code, but I just need to look for the specific one that I want to make some change. Okay, so we have these points occurring that help to building the model. Another point is uh, some models are too good in specific modules that some researchers start to get, for example, weather from one model, management from another, and the soil water balance from another model, and start to building models with more information and looking for different work areas and building a model with more efficiency to make simulation based on the scope of each model that you are using. In this point, the code program, it's important to look for validate the unit terms. So if I have solar radiation, for example, I have megajoules per square meter per day. And if I have the radiation use efficiency, I need to look that when I use solar radiation and use efficiency of radiation use efficiency, I have the same unit to make the calculation from this input and from this parameter to get the correct output. For example, I have the radiation use efficient where the biomass is calculated based on grams by megajoules by day, for example. So my output will be the grams of biomass for square meter. So in this process, you need to look at this. Another point that is very important for modeling is to look if the system it was validated in terms of energy and mass. What this means that nothing can be lost or created out of nothing. So if I have an input of rainfall, for example, this rainfall need to go to some place, to soil or to crop, and after this input will be a state variable, and after you're gonna be this is gonna be an output for the system. So between input, state variable, and output, I need to have this totally value always available for the crop model. If I put 10 liters of water, this 10 liters go to the soil, and after I'm gonna lose 5 by draining and 5 by crop transpiration. So I put 10 go to the soil, 5 I lost by drain and 5 by transpiration. My system, it's okay. I don't create new water or lost water for some output that I don't know in my model. I need to look at this to see if my model is working well. And after I make this program, I can use different programming language. So the best one is the one that you know. We have a lot of example here. We have models building in Fortran. So this art is building in Fortran code. We have the Python for Monica and different approach depending on the developer for this program. Okay. Another important process for the crop model development. So I have our aims, I have my hypothesis, I have my mathematical formulation that I just build an equation, but I don't put value for this equation. I can program this with parameters, with equation using general information, but there is a point that is very important and probably after, after all this mathematical formulation is the most important point, that is the parametrization. The parametrization of a model is the way of obtaining parameters. We saw in the last class that we have these different parameters between species, between cultivars, which are usually constant values that make up the mathematical function used to describe the system. So I did my mathematical formulation, how our system is affecting the outputs and each inputs I need. And after that, I have this requirement of to put values in these parameters to represent our crop or our system. Basically, most of models divide the crop in parameters related to the species and parameters that relate with cultivars. Okay, the parameters related to species, they are the parameters that has less variation between these different plants. Example, the chemical composition of the plant. It's a condition that vary less between the cultivars, for example. Even I can have some difference. And another point that after speech, we have the cultivar parameters. That are the parameters that have a great variation, and I need to make calibration or get the parameters for this specific cultivar. We're going to see in the DSAT class that we have the speech parameters that you don't change and the cultivar parameters that you can adjust for your cultivar. And here you have example, the thermal time duration for crop phase. It's something that changes a lot between cultivars, and you need to look at this to make this difference and make the model able to represent this. So when I am building a model, I need to define each parameters you change less or more, and each parameter I need to put there to make this difference between cultivar. Okay, and how we can get these parameters from our cultivar. There is three ways to make this. The first one is literature, so it's a good point to start. We need to look for readable source and evaluate source, so I can get this from reference literature, but I need to get from a good literature this way. Here we have an example for radiation use efficiency, where you have these different values for different crops, and I can use this condition here to start my model. Another way is based on measured. So I have an experimented field. I use protocols for making these measurements, and I get the value for radiation use efficiency. What's the problem for this approach? I need time, it's laborious and expensive to make all these measurements for building a new model that I have interest. And the third point is calibration, that is based on trial and error. What does this mean? I have the model building based on different equations with different parameters that have a initial condition that represent a average across different cultivar or for that species, and I can start from this point. I don't measure, for example, radiation use efficiency. I don't know which value is for my cultivar, but I have biomass or yield being measured at the field. What I can do is try to change this parameter related to radiation use efficiency to reduce the error from measured and simulate values for biomass. I will change many times and repeat this process for many times, and I can get a correct value for this condition, because this we call trial and error. And in this process, I have two steps that need to be done. That in the first moment, I will get two-thirds of my data to make this calibration. So I change the parameter to trying to reduce the error, but I need one-third of data to just to see if after my calibration the model is able to simulate this condition, and it's not associate only a, a change of my parameter to get the right that results. What is the problem for this calibration way to get the parameters from the models? We can take a parameterization to empirical trend, so we have interaction between soil and plants sometimes. And my aim is to simulate yield. I can get wrong leaf area index or biomass or harvest index, but I need to get yield right. This is a problem because when I build a model with a dynamistic way, I need to get right any process in the model. For example, I need to get the right leaf area index, biomass, and the end of the process I'm gonna get yield correct because a consequence of right things that I do in this calculation process. I can have interaction between parameters. So if I change leaf area index and change radiation use efficient, I can change the biomass in a different way. So if I increase the FRI index and reduce radiation efficiency, I can have the same condition if I increase the radiation use efficient and reduce the FRI index. So you need to be careful with this interaction between parameters. And the last point is that parameter in ecology and environment size are not known to be exactly value and can change constantly. So if I measure radiation using fission from my experiment and measure for another experiment near here, I can get different values. So it's hard to define the correct value because you have this natural change for this condition, or I have factors that I can control in the experiment that can change the results for each one of these measurements. Okay, and other parameters, most of the time the calibration is applied when I have some parameters that is too hard to make a measurement or obtain this information from literature. I want to see that we have this limitation for a root. It's hard to find information about root, and you need to look for this interaction in the model, and each parameters you need to calibrate locally for values of parameters that I don't know exactly each one is. So always we need to understand how the models work, and each parameters we need to look carefully for my local condition, or each parameter I can get from the default of the model, so we can define what is best for each calibration. To improve this process of calibration, a lot of statisticians start to develop algorithms to make this calibrate process in an automatic way. For example, using Gauss-Newton or Bayesian knowledge, instant I get the data from field, make this calibration, and change A and B parameters to get the right yield. Now these parameters can be estimated using algorithm, where this algorithm looking for my data and the outputs and comparing this based in some assumptions that I can put in this automatic processor. They define the parameters for A and B. What I need to look carefully is that sometimes, because it's only a statistical approach, there is no physiology or knowledge about this interaction process. I can get values for A and B or any parameter that I'm calibrating out of the range measured in the field. Okay, during our class about this act, you're gonna learn to use this for calibrate one cultivar based on these outputs and in these algorithms to make this calibration. One approach that I like to do, and we have a lot of studies showing, is the sensitivity analysis, where I do this to understand how my model responds to some parameters. Here I have two examples where this author changed for different parameters here to less 10 or plus 10% of the value of the parameter and analyze how the model responds change yield based on these parameters. For example, here when the field capacity was increased in 10%, the yield increased 8% for each 10% of increase in the field capacity. In the same way, when field capacity was reduced 10%, the yield reduced 0.4%. Another example here, the author evaluate how the root elongation rate change the error in the grain yield. You can see here that when I have this value here near 3, I have the lower root mean square error, indicating that I can use this value to as a parameter in the model to make different simulation for this condition. And the last step, after evaluate my aims, get my hypothesis, make the mathematical formulation, program this general code, define the parameters in the model, I can evaluate to see if my model is good enough and get the correct simulation. We have two points that need to be evaluated. The first one is the transparency. Refers how easy it is to understand the model. So how my model works, how I get information of this model, how the model works, what information I need, how the model makes some simulation. All this information are very important for the modeler because we need to know what information you have in the model and how this model works to understand how to work with this model and make a simulation more right for our system. Another point is the robustness, is how close the model simulates the observed values. So I make my experiment, get my input information on there, put in the model, and how the model are simulating this environment. It's good or not, based here in the complexity of this model. And in this process, we have the validation that you're gonna verify if the simulation performance represent the system that the model was proposed to represent with adequate response to the local condition. So if I have here a model building for a system, how good is this model to represent, based here in weather and soil, to represent my field that I wanted to make the simulation. And in this process, I can have data from different experiments. And when I work with calibration, we assume that 2/3 of the data are used to calibrate, and 1/3 is not used to change parameter, but I use this data after I finish the calibration, just to look if my model is simulating the right build or any other process that I get from the field. Here we have an example where we have the model evaluating the yield response for the calibration and after for validation. So that you have here near 1000 samples for calibration and near 140 samples for evaluation, showing that when I change the parameters, the model work well, and when I just simulate the yield, this model work well too. For this process, I can use statistical index or graphs to represent my model performance. Here we have a different example in this book that you have access, where we have a DBS, mean square error, root mean square error for this process, relative root mean square error are index very useful for us to understand this performance. We have the modeling efficiency, that is an index that have been used extensively now for evaluating model, and other different type of index that you can use. We also can use graph to make this analysis of performance. Here we have the measured grain yield, and here we have the simulated grain yield. You can see that these models are getting the variability from the field, where we have this variation. These are occurring in the model, and most of points are near the line one by one. And here you put some information, additional information to represent how are the index across this condition. We have this temporal analysis because most of model have this simulation occurring by day, so I can get the output of this variable status, the state variables from each day. So I can compare here. We have 4 models, and the point are the measured biomass. I can see how my model is simulating this curve across the crop cycle under rainfall and under irrigate condition. We can use graphs about deviation and errors in the system. So here we have 5 models and the average of model for different field condition, and you can see for each model how is the range of this error and where this model is get more or less wrong. So you can see here in this example that this model have higher range for this condition, showing more a positive deviation, while the other models is more stable between these different values. Here also you can plot the measured yield with the relative error and saw if you have some tendency based on the measured yield, what is happening for each one of the model. And to finish our class, we have this question: what is the acceptable level of error? Here I bring my work that we did evaluating 5 models and the average of 5 models in different phases of calibration based on the parameters that we change, and you have these different index. So what is the acceptable level of error? We don't know. We need to find our M, if this error is acceptable for us based on what we want to evaluate. We need to look for other studies that evaluate the same model or a different model, and based on this information you can bring details if your model is good enough for the proposal that you are developing. Okay, so here example that you can use different statistical index to evaluate the model and compare the model across these different models and different studies to evaluate the performance of the model. Okay, thank you. See you. Bye bye.